Well, hello, this is Steve Samuel from Design Visionaries, and I'm proud to bring you a video about some modeling tools that I think are really compelling. And as you can see here, I've got a geometry that is somewhat reminiscent of an elephant's trunk with polka dots or pimples. And in order to build this kind of geometry, there's some nice sweep techniques and some pattern techniques that I think you'll be interested in. So, what I can say is, in order to create a piece of geometry like this, you might start with a sketch that really emulates the center line of the shape that you want to create. And the shape that I'm creating here is a spline. And as you can see, what I've done is I've created a spline, but I've also created an offset of that spline, a slight offset, for reasons that will become obvious in just a moment. So once I have that spline, which is the center line of the shape, then I created an offset curve. And the offset curve starts at a high location, or a greater value, and ends at a smaller value, but then oscillates in between. And the way I got that to happen is by creating a law. If I say Control E, you'll see that there's a law that I've created. Now the law is kind of interesting. I have a height 1 and a height 2, and that is roughly, not roughly, but almost exactly, the distance between this vertex and the beginning of the offset is h1, and then h2 is the distance from the center line to that offset. And then I've got a law that I've created, which is the radius plus this function called bump. And bump is 0.05 times the sine of the number of lobes, right there, times 360 times t. And so I've got a value, or I have a variable called the number of lobes, n lobes. I've got a variable called r, and as you can see, r starts at h1 and then decays as t goes from 0 to 1. See, so t is multiplied by h1 minus h2, and then I'm adding bump onto the end of that, so that's the radius, and then t is a variable that's evaluated from 0 to 1. So that's just how law curves work. And so I use a lot of law curves in the things I do because they give you such incredible power. So as you can see, there's bump, there's this law called r plus bump, and that's what I'm using to drive this really cool oscillating, decaying offset curve. So if I go to the offset curve, you can see that my choices are law controlled, and I'm using a bi-equation law, and my parameter is t, and my function is actually law, and that's how this little function, or this little offset curve, starts at a high number and then decays. So then I create another sketch, and that's a sketch that is perpendicular to the drive curve and is also catching the radius, or its radius is set by this offset curve. And then I do a sweep. So the sweep is really interesting. The way the sweep was done, I did a sweep swept, of course. So my section string is that circle. My guide string is what I've been calling the center line. But we also need an orientation method, and the orientation is another curve, the other curve being that offset curve. And what the orientation does is it sets how the section is going to be held perpendicular to the curve as it goes along. And then there's a scaling method, and the scaling method is another curve also. And what happens is that section is scaled by the distance between the drive curve and this quote unquote another curve. And we're using the offset spline as the another curve. So that's why you get a nice little piece of geometry like that. And then I put a helix. I put a helix on the surface basically. It's not really on the surface, but it's following the drive curve. But the radius of the helix I'm controlling with that same law. If I double click on that, you can see that the radius is controlled by equation. The parametric variable is t, and the function I called it is law. And that way, this nice little helix is really following the surface. There's little places where it comes apart, but that's probably because my math was not perfect. And as you can see, the helix just follows along. And then I put a sphere on the end of that helix, just like that, and united it. And then I patterned it along that spine, or that helix. And when I patterned it with a pattern increment. So it started at large. It started off as a large, I think it was 0.5 diameter sphere, and ended up much smaller. So there's 220 of these little spheres on here, and I basically put in a pattern increment of negative 0.25 divided by 220. So what happens is the sphere starts at 0.5, it ends at 0.25, and it decays linearly every 220 spheres. So there you have it. I did a delete face because I didn't want those top two to be there. And then of course Control W gets rid of the curves, like that. And what you're left with is this really amazing looking solid. It looks like an elephant trunk. It's reminiscent of an elephant trunk, the kind of elephant trunk that you might see when you've been drinking a lot. Anyway, I believe that creating geometry like this really hones your skills, and even if you don't have anything right away that uses these techniques, I find that at some point there will be a need for some production thing. Maybe you're working on a nuclear power plant shield or something like that, and you've got something that decays and has to have this ripple in it, or maybe it's how you create, you emulate the surfaces of a boot that would be around some flexible tube that diminishes in diameter. Whatever, to have the skills is really important because you never know when you're going to need them. So the skill of doing a pattern with a diminishing diameter increment is there. The law curve is there. The offset curve. So all of these things give you incredible power to do very complex geometry. Thank you very much. This is Steve Samuel from Design Visionaries, and hopefully you will check out our YouTube channel. The Design Visionaries YouTube channel has a bunch of videos that show you how to do all kinds of really cool geometry. And check out our website at www.designviz.com. Thank you very much, and happy modeling.